So now we're moving on to the equilibrium topic, and we have briefly touched on this before in the energetics unit, where we talked about if there is not a huge difference in enthalpy between the two reactions, and there's not a huge difference in activation energy, then the two reactions can easily swap back and forth. Okay, and so that's what this is a typical of an equilibrium reaction. And so when you have an equilibrium reaction, what you have is some proportion of this, maybe, like 10, 20, 30, 40% is on one side, and then a certain proportion is on the other side. There's one other notable thing about equilibrium is that also you'll find if the enthalpy is favored on one side, you'll find that the entropy is favored on the other side. And so if you have a careful look here, you'll see in this equilibrium reaction, you'll see that here it's favored for entropy, and on the opposite it's enthalpy. So again, this one's favoring loss of heat and loss of chemical energy is heat that's going to dissipate, and this one's favored two particles, more unstable state. This one here, you've got 4 moles of gas rather than 2, so this is entropy favored, and then loss of chemical energy as heat is favored on this side. And so you'll see that there's a tug-of-war between entropy and enthalpy. So let's move on. So we need to do the official definitions. Equilibrium is achieved when both the forward and reverse reactions are occurring at the same rate and the concentrations of products and reactants do not change. Okay, so in physical equilibrium here, you'll find that this is a physical reaction here. So the rate of evaporation is equal to the rate of condensation. Okay, we also have chemical equilibrium. And so that occurs, for instance, with water. And so the rate of H2O that dissociates into H plus and OH minus is also occurring at the same rate that is combining. Okay, so it's physical and chemical. Make sure, of course, you do these 2 half arrows as well. So make sure you know if something's in equilibrium. Okay, now equilibrium graphs look like this, and so they look like a rate of reaction graph. So they're very quick when the concentration's high, and then when they're close to evening out, they go here. So this one's going down to 0, so this one is a completion, and this one is half, what is it, 20, 26, 30, 1/3, 2/3, and so that's a rate of reaction graph, and around this point here, they've reached equilibrium, where they're turning into each other at a constant rate. Make sure you check to see whether it's homogeneous or heterogeneous, because that will affect calculations later on. You can see this one has 2 different states, 2 or more different states, so it's an equilibrium, heterogeneous equilibrium. Now, if it's doing that, you've got to make sure it's a closed system, otherwise this will keep coming off and the reaction will actually go to completion. So the last thing we need to look at is you have to make sure it's in a closed system if it's to reach equilibrium. And so an open system is you always have energy can go in and out unless it's an isolated system, which I don't know if exists. I think the universe theoretically might be an isolated system. But energy can usually get in and out, as it can in this bottle, light can go in and out, for instance, or heat. But if you close the bottle and matter can't get in and out, then that is a closed system. So that's what we need for equilibrium to be established. We can't let matter escape and then the reaction go to completion.